today, and then I have also 4 sessions tomorrow. So we'll start conditional constant propagation tomorrow. We'll do some exercises, hands-on exercises now. Okay, so and there will be some kind of exam also at the end. So there are few questions there as well, but I am not put any proof questions there. So that's why we'll do proofs kind of things in this room, in this classroom. Okay. Okay. So as I said, there is a change of plan. Rather than starting the new topic, we will solve some problems now. And this is the first question for exercise. And so it's about proving certain properties. So we have this habit of reading everything from slides or books and assuming that it is true. But that's not a good habit. So we'll have to have some exercises. So what kind of proof techniques do you know? What all proofs have you done till now? What are different ways you can prove something? Yes? Proof by induction. Very nice. Proof by contradiction. Anything else? No, but that is just a breaking down a big proof into smaller proofs. But finally, you have to have some techniques. Okay. So there are various ways. Okay. So what do you think will apply here? So again, anything when you are trying to prove something, first thing, are you convinced about the statement? Yes, go ahead. So that is by contradiction. Okay, you assume the reverse of what is asked and then show that reverse cannot happen. Okay, so tell me. So first thing, are you convinced that this is true? Sometimes the statements may not make sense. And again, because here we know it is true, so it must be true and I am convinced. In real life, that will not happen. Real life, you will have to have some conviction and then only you have to go and start proving it. And As a result, you might either prove it or you might come up with a counter example, or you might not be able to do it like classical P and P problem. Okay, you don't even know what is it true or is it its reverse is true. Proving is the second part. You don't even know whether it holds. But this is something which definitely is correct, which is true. Then how do we proceed? So, what is your name? Jayashri has said she wants to try it with by contradiction. Oh, thank you. So how will you contradict? What do you do? So if you have to contradict, you have to have a statement first. So I missed my tea during the break, so I am having it now. Sorry for that. Yes. So I mean it's easy, right? Okay. So you have just put not in this, so that becomes a very complex statement. Take a simple statement. Okay, what will be an immediate dominator? So given a node, if it has an immediate dominator, what will be the property? So X has an immediate dominator Y. So can there exist any other dominator between X and Y on some path? No. That is the nearest. But again, this is like you are saying some way. Can you prove that? Or can it happen there are two different immediate dominator? What would go wrong if there are two immediate dominators? Let's say D1 and D2. So either both will not be dominating, or no, there is something else can happen. You can prove that D1 dominates D2 or D2 dominates D1, which means one of them is not nearest, which means one of them is not immediate. Okay. So you either prove, basically you have to prove all possible cases. One is they are not even dominator, other is yes they are dominator, but one of them is not immediate. So you have to get all these contradictions. How will you start? So you have to prove some kind of ordering among dominators. So given two dominators D1 and D2 of a node X, can you prove some property? D1 could be equal to D2. Is it always the true case? No, right? There can be multiple dominators. No, not immediate. I'm just talking about dominator now. Okay. But now we are talking about, so there is an entry node, there is a node X other than entry, and you are saying there are two dominators D1 and D2. What is the property? Every path from entry to X has to go through to D1, and similarly every path from X entry to X has to go through D2, which means every path from entry to X has to go through both D1 and D2. And let's assume D1 is not equal to D2, because otherwise the case that those are all trivial cases. D1 is same as D2, then you are kind of not even proving anything. So what we are saying, D1 dominates X, D2 dominates X, D1 is not equal to D2. Okay. Now what else can you say? How can you say that? These are given. These three things are given to us. Now you are making a statement. Immediately ask, can you prove that? How do you start? Where do you start? Only thing you know is on every path from entry to X, D1 exists, D2 exists. On every path, no matter how you take it, there will be D1 somewhere, there will be D2 somewhere. That's fine. There can be two paths. I can have a path like this. There's D1, there's D2. I can have any number of paths. Yes. See? No, no, look at this. There are hundreds of paths. Every path goes through D1 and D2. D2 also dominates X. I can have hundreds of paths here also. That I agree. No, earlier you said multiple paths. We cannot have this. That also I agree. What does? But this is all pictorial. I might have been missing some case. So, still you are only saying what we are given, that D1 dominates X, D2 dominates X. Every path, yes. There can be multiple nodes. Yes. Again, don't confuse with immediate dominator yet. We are just talking about dominators and their property. Yes. So finally what, okay, good. Anything else? Anyone wants to correct a little bit what she is saying? No, don't go into other things. Just stay with dominator. No, but then, see again, this is given. Why you are saying D1 does not dominate X? That I am not able to understand. This is given, D1 dominates X, D2 dominates X, and D1 is not equal to D2. These three are given to you. Now what can you say? There can be multiple paths, there will be hundreds paths. But and D1 is not equal to D2. Now can you reach that? So can you say there is some contradiction? What you want to say now? Okay, so at least she is quite close. What you can prove is either D1 dominates D2 or D2 dominates D1. Okay. No. From which statement? You are always talking about X. I am only talking about D1 and D2. No, go ahead. That's fine. I think you may not have explained it properly. So So again, you are making a statement. This is what I am saying. You are making a statement. How to prove that statement? Okay. So now you made a statement, this I said, yes, this is okay, but you have to prove this. This is not possible. How do you prove that? But then if even if this is possible, in one time I have this, another time I have this. So even stronger cases, if this is there, then this is not possible. Only one of these two cases will be possible. So either D1 dominates D2 or D2 dominates D1. It cannot happen that on some path D1 comes before D2, on some other path D2 comes before D1. Now how do you prove that? So is the problem clear now? At least there is a property which says if both D1 and D2, two different nodes, dominate X, then either D1 dominates D2, which means every path from entry to D2 will go through D1, or D2 dominates D1, every path from entry to D1 goes through D2. It will not happen that on one path D1 then D2, on another path D2 then D1. Conceptually that is also domination. Sometimes D1 comes first, D2 comes first, then X comes, and then D2 comes first, D1 comes first, then X comes. But that is not possible in our path. Okay. It can happen that D1, D2, D1 something, that is also okay, but on every path there will be an occurrence of D1 before D2 or the other case. Okay. So without loss of generality you can you prove that D1 will always dominate D2, other case is similar. So on one path D1 comes the first occurrence of D1 and then an occurrence of D2. So take an acyclic path from entry to X. Can you say something? And assume on that path D1 comes first. And then can you prove that D1 dominates D2? So take an acyclic path from entry to X, acyclic you understand, assume on that path D1 comes first, okay, then D2 comes. Now because this is an acyclic, they will occur only once each, right? And there will exist such an acyclic path. If there is a cycle, you just cut down some of the edges, remove some of the edges, it does not matter. So an acyclic path has to exist. Okay. Now in this path, D1 comes first, D2 comes later. Can you prove D1 dominates D2? So now you take a contradiction.
So first, like from the given D1 dominates X, and from the second one D2 dominates X. So that is like we can say that first one is actually the superset and the second one is the subset of that superset. So from that,
please don't introduce unnecessary. Why set and superset came into picture? What is the set here? Path. We are talking about path.
means D2 lies on the path of D1.
Yes. So D2, I am taking, you are picking a path. You pick an acyclic path from entry to X. Okay, and you found that on this path D1 comes first, then D2 comes. You pick an acyclic path from entry to X that you can pick. Go ahead, please.
Every path to D2 has to pass through D1, so D1 dominates D2.
That will prove. Okay, I think you got it. So now we have to prove it. Okay, but let's first explain this. See, I am saying D1 dominates X, D2 dominates X, which means every path from entry to X goes through D1 and D2. Okay, this is clear up to this point. Both D1 and D2 have to be there on every path. Now there has to exist an acyclic path. Is that clear? In graph, if there is an acyclic, there is a cyclic path from A to B, you can always get acyclic path from A to B. Just remove the reverse edges. Okay, just cut down some of the edges. So now I got an acyclic path also. Next, now this is an acyclic path from entry to X, which means again D1 exists on that path, D2 exists on that path. And just by looking at that path, I found out D1 comes before D2. So this is the property of the path. And you can also argue D2 comes before D1, one of the two. But the moment I see D1 comes before D2, now I make a claim D1 dominates D2. Okay, now I make a claim. This is not given anywhere. Looking at the path, seeing D1 comes, then D2 comes, I make a claim. Can you prove this claim? I think he can prove. He has made it before me. So he has that. Yes, please. वो ले लो second.
So can we say that the entry has to dominate all points?
That
so,
is given. Yes.
So the entry won't be able to dominate X until D1 dominates D2.
No, again you are reiterating the same. So how do you prove that? Now you have to prove. That statement exactly means that D1 dominates D2. So how do you prove this? So at this point again you have to start with contradiction. Suppose D1 does not dominate D2. What does that mean? There
exists an
another
alternate
path from entry to D2
where D
does not go through
D1.
But now this image itself tells you something. Now I have a path from entry to D2 and this part does not contain D1. Remember, that is why acyclic is important. If it was cyclic, DT1 could exist. Since this is acyclic, this path does not contain, this part does not contain D1. Is it clear to everyone? Remember, that is why cyclic or acyclic is important. Cyclic path, I could have a D1 here as well as here. This is acyclic, so there cannot be a D1 here. Okay? Now the D1 is not here, but then I have found a path from entry to D2, D2 to X. There is no D1 on that path, which means there is a contradiction because I am given D1 dominates X. So that means D1 has to dominate D2. I will come again, sure, why, that's the thing. We are given D1 dominates X, we are given D2 dominates X, and we are given D1 is not same as D2. Okay. Now, because D1 and D2 dominate X, you pick up a path from entry to X. Okay. Can you pick up an acyclic path? There are no cycles, there are no back edges. So that no node is repeated.
Why specifically we are going for a cyclic path?
Okay, I will come to that. Suppose we take a cyclic path. I want to say, at least see, even if it is cyclic, it's not that a problem. From D2 to X, I do not want a D1. That is the important thing. Any cyclic path, you can always convert into an acyclic path between those two nodes. What is cyclic path? You are going onto edge, then you repeat, rotate, and then again you take something and go out like this. Okay. So I can always delete these edges and just keep this part. Okay. So I need, in fact, I need any path where D1 and D2 are not repeated, or at least one of them is not repeated. But then proving all those things are difficult. I know an acyclic path exists from entry to X, which means I can pick up that path. Now when I look at that path, I find out that D1 comes before D2. And this is without loss of generality because I can do reverse also. I can again prove if D, so I say if D1 comes before D2 on this path, then I can prove D1 dominates D2. Up to this, things clear? Yeah. Now, so next step, I have to prove D1 dominates D2. So I start with contradiction, that D1 does not dominate D2. What does that mean? From entry to D2, there exists a path on which D1 does not occur. So I have another path from entry to D2 on which D1 does not occur. But then what does that tell me? I can go from entry to D2 and I can go from D2 to X, both without D1. So I found a path from entry to X.
So it's a contradiction.
So it's a contradiction. So if it is a contradiction, then I cannot have such a path, which means on every path from entry to D2 I will have D1, which means D1 dominates D2.
Got it.
Okay. Now if D1 dominates D2, So now this is just one part of the exercise. Okay, we have just proved that if a node has more than one dominator, then there has to be an ordering. Okay, now and this is a complete ordering. You can always say either D1 is greater than D2 or D2 is greater than D1. Greater in the sense DOM relation. Okay. Now once you have that, so then again this is all mathematics. If you have an order and if you have a finite set, there has to exist a minimum element. That minimum element is your immediate dominator. Whosoever is closest to X on this path which is dominating, you can talk about D1, you can talk about D2, D3, D4. Whosoever is closest to X, that will be your immediate dominator. Okay. Now there are two more things. One is except entry. So clearly entry, you can show that entry does not have a predecessor. So entry cannot have an immediate dominator. Immediate dominator has to be something other than entry itself. So that part you can prove, and you have to prove that every node has a unique dominator. So we have proved that if it exists, it is unique. Can it happen that a node does not have any dominator? In normal graph, yes, it can happen. In CFG with an entry node which is dominating everything, so you have one dominator, then entry itself becomes the unique immediate dominator. If you have two dominators, you have an ordering, so second one becomes your immediate dominators. If you have 5 dominators, the last one becomes immediate dominator. So both the conditions, that there is an immediate dominator and there is a unique immediate dominator, and entry does not have any dominator, all these things kind of work out. Okay. Once again, the general rule is in every graph, if a node has a dominator, then it has a unique immediate dominator. So existence of unique immediate dominator is question mark in general graph. Because in general graph I can have two nodes sitting isolated, one here, one there. So there is no dominator, and there can be an entry node sitting at the third place. They are not connected. Disconnected graph, there need not be a dominator, because entry is sitting in Agra and node is sitting in Lucknow, right? But here, because entry is connected to everybody, you have to have a unique immediate dominator. Okay. Second one, proof is also very similar, a little more involved. Let's get some idea and then you can try it if you get some time. So basically all these proofs come into when you try to prove your SSA form is actually, all those optimizations or analysis are correct, proved correct. Doing the full proof is difficult in any class, so I just do these small proofs to give students idea what they have to expect whenever they are writing their own their own new analysis or optimizations. So once again we are having a CFG. I have a node X, I have a node Z, and X and Z are different. There is a path from X to Z, and on this path there exists a node Y. Now Y can be same as Z, there is no question about, there is no constraint. Okay, X and Z have to be different, but Y can be same as Z. The goal is on this path there exists a node which is not dominated by X, which means there is a separate path. Okay. Now there is a totally unrelated claim made that there exists a node N in the iterated dominate frontier of X that dominates Z. Okay. So there is an iterated dominance frontier of X. There exists a node there which dominates Z. So which also means that it has to exist on this path. Okay, though I am showing it slightly separated. Okay. So let's think about first case when y and z are same. So this is our z. So there is a path from x to y. Y is not dominated by x. Okay, but there exists a path in iterated dominance frontier of x which will dominate y. So let's forget about the general case. Let's take a simple case. So note that one simple, again, special case is maybe y itself is the part of of dominance frontier because its predecessor is dominated by x, y itself is not dominated by x, strictly dominated because they are different. So y belongs to df plus of x, which means y dominates itself. So this is, I mean, trivial. One of the cases is easy to prove, but in general this is true. So how will you work on such cases? No, it's not a contradiction. It actually says it can be same. X and y and z can be the same. They can be different also. It's not necessary that they are same. So this is all this influence of your assignment which is going through in SSA form. So you have to prove that something happens so that you insert if you insert a new definition, its effect will be reached and so on and so forth. Okay, so it looks totally unrelated, isolated kind of thing. What can you say generally about this path? Yes.
We can say about n that it will be in the path from x to z.
From
X to z.
What will be on the path n?
Yes, that is a claim.
Yes, that you can do. Whether it helps or not, it's a different thing.
So if we take node n in the arbitrary path from x to z, then
But
we can
on that path, we need a y which is not dominated by x. Arbitrary path, you won't be able to prove that.
okay, so it's a path where y is the path that x takes to z through y. So there should be an arbitrary node n
Hmm?
which dominates z.
Yes.
So that is the case.
But how do you prove that? That's the proof you have to give. You have to prove the existence of such an n. See, typically when you have such cases, again you need some kind of ordering and you have to keep snipping down the path. Currently we don't know how long this path is.
So, can we say, okay, can we say to begin with, y is actually equal to z?
That is one case you will prove.
One case, and the n, we are not sure whether the n will dominate y or not. but n is already not dominated by x, and x doesn't dominate y as well. So
Yes.
can we consider n and y could be the same?
They could be.
So n dominates itself, so n dominates z because n is equal to y is equal to z.
No, no, but where did you get that y dominates z?
No,
I never said anything about y and z.
not y dominates z, y is equal to z.
Y is equal to z. So okay, so all three are you are saying same.
So it dominates itself, so n is equal to z. I mean, n dominates it. So because n is equal to y is equal to z.
But then have you proved that n belongs to dominance frontier of x?
But because it's given there that there exists a node n.
Belonging to df plus. Within df plus, iterated dominance frontier.
Then I think y belongs to the dominant frontier of x.
No, it does not say anything. It just says x does not dominate y. It does not say y belongs to dominance frontier of x. That's the thing. We have to prove it. That's the question.
And then you can assign n equal to y.
No, but then again, see, you are jumping. There is nowhere we are proving y. Are you saying y and z are same? No. So then you have not proven that y dominates z. So how can you say n is same as y? How will that help? So you have to prove two things. There exists an n and n dominates. I mean, existence is easy, just, but n dominates z also you have to prove. So what can you, okay, let's think about, even I have to think about it a little bit. I did not give much thoughts. You have to think about a sequence of nodes, something like this. The last node is z. So let's say this is the path. Okay. So now clearly there exists some node y here which is not dominated by x, which means on this path there will exist some node xi such that its parent will be dominated by x, but xi itself is not dominated by x. Can you say that? Don't go fast. I don't know what is the answer, so let's do step by step. Let's first think about such an I. Is it possible that xi minus 1, basically the predecessor, is dominated by x and xi itself is not dominated by x? Can you prove existence of such an I? How? So we know somewhere there exists a y which is not dominated by x. So what is the predecessor of y? Is it dominated by x? If not, then we keep moving backward. Finally, x is dominated by itself. So you know that the next guy here, either it is dominated by x or not. If it is not, we have found an I. Are you getting this? See, x dominates itself. And we know y is not dominated by x. These two things are known, given, right? So let's just look at y. What is the parent of y? Is it dominated by x or not? So there are two cases. Suppose parent of y, a predecessor of y, is dominated by x, right? Then I got my xi will be y, its parent is xi minus 1. Suppose its parent is not dominated by x, then I check parent's parent. So I becomes parent, I minus 1 becomes parent if parent is grandparent is dominated by x. Okay, I have to keep moving backward, but then I have to show that it will stop. It will definitely stop at x because x dominates itself. So you cannot keep going grandparent. Finally, so maybe x1 is your the choice. So which means on this path there exists some node xi which belongs to the dominance frontier of x. Okay. You replace x by xi, look at xi's dominance frontier. Okay, and you have to keep doing this. So exact thing I will have to check, sit down and do it. What happens? Your path size reduces. Okay, and finally you will end up in a situation where every node is. So finally you will end up at z itself, or you will find a chain where everything is dominating z, and that xi will be part of your dominance frontier of x. You have to shorten this path, keep shortening, and since this is again you have to take an path, a cyclic path only. Okay, if this path p is cyclic, you remove the cycle. You take a p prime which is an acyclic component. So in other words, you can assume without laws of generality that p is acyclic. Okay. Okay, any other question? Yes. So look at this, work on this. I will share the paper also, you can see the code there also. So at 3 what happened to question 3? This is an interesting question. First, is the question clear? Now create a group of 2 and discuss this. It will be good if the 2 people have different opinion. You can create a group of 3 also, not a problem. So sometimes, so this is a well-known thing. If you have a statement and you don't know whether it is true or false, to prove the statement you have to give a solid proof. But to show that it is false, you just have to give a counter example. So always try to get a counter example, that's easier. Only one example is sufficient. You cannot prove a statement by giving examples. You can disprove by giving a counter. So then the example is called counter example. What is your feeling? Are they equivalent or not? Okay. See, others should also interact. I don't want to be sitting in this corner only. So, what is your name? Huh? Nikhil. Nikhil. Okay. So, Nikhil, Jayashri, and some people on this side are winning the contest. They are interacting so much, but others are not that much. Morning session, you were quite interactive. Now, you have taken a back seat. Why? क्या वो मिल गया? So we have actually done this case in the morning session. So what kind of node will differ in these two definitions? Only B part is different. What is the difference between strict dominance and simple dominance? So think about it, and then you will be probably be able to get it. I said, I was talking to them that morning session when we solved our example, which was quite complex, but some case came where this would have made a difference. Yes, please. मेरा नाम क्या, मैं थोड़ा भूल गया, लोक कुछ था. Your name? Lukman. Okay, Lokman is Lukman. Okay, Lukman. Why do you ask? Why are you asking me? So that is the case which will turn out to be the problem. Yes. Of course, this is. You got it? Okay. See, what is the difference between dominate and strictly dominate? In fact, that's the only difference case. Mike. Go ahead, use the mic. So when do you say N strictly dominates M versus N dominates M? Domination, let's say what is the difference between, or in what condition N strictly dominates M?
They mustn't be equal. They mustn't be equal.
So only case where they differ, dominance and strict dominance, is when you are talking about same node, N dominating N, X dominating X. So X dominates X always, but X never strictly dominates itself. Okay. So a node dominating itself is the only differentiating case. So which means if you are thinking about creating an example, you have to think about dominance relation between, or dominance frontier relationship between X to itself, X being in dominance frontier of itself. That is the only differentiating case. If X and Y are different, these two definitions will give you same result. Only when you are talking about X in dominance frontier of X, it will cause issue. Now when will you try for X being in dominance frontier of itself? What are the two cases for dominance frontier? First is predecessor has to be dominated. Second is not a strict domination. So again, when you are talking about X and X, second condition is trivially true. Okay. So first condition is predecessor of X must be dominated by X. Okay. So which means, again, the way it is happening, the predecessor of X, okay, will have X as its successor. Okay. So that is the interesting thing. So in other words, you have to have a back edge, loop. So in case of loop, these two definitions will not coincide. They will produce different answer. So the simplest example is self loop. Even though it is not necessary, you can have any longer loop also, like we saw in the morning. But the simplest example is having a self loop and compute dominance frontier for this very simple example. Let's say our node 1, node 2, and you don't really need node 3, but just to, visually it is appealing. Okay, dominance frontier of node 2 will differ if you use these two different definitions, because 2 does dominate 2, but 2 does not strictly dominate 2. So the 2 will produce different answer. And look at this, in this case M is 2, N is 2, predecessor of M or N is also 2, so everything is, the single node is playing all the roles, and that is why it is important to have not strictly dominate. Okay, so please complete this exercise. Let me see if we have any other questions. Okay, so this is something, again, I don't know, we have not done it in very much detail, data flow analysis, but this is another interesting case. I think we should solve it. Okay, what I have is a very simple data flow framework, like available expression, live variable. I have some analysis which is only interested in finding values 2 and 3. Okay. So some of this we have not done, so it's probably I thought it will be covered by Professor Khedkar. But here is a flow function which is not monotonic, this flip x. It kind of rotates between, you take 2 it becomes 3, you take 3 it becomes 2, so it is not a monotonic. So again, I don't know how simply I can explain to you, but if you have your control flow graph, okay, this is I am doing very informally, so please skip if you are not able to get the intuition. If I have a flip x kind of function here, okay, so in data flow analysis you will be iterating over this edge. So first time maybe your initially x is 2 or the information is 2, after flip x it becomes 3, meet is maximum of 2 and 3. So on this path my value is 2, on the other path value is 3. So what will be the output? 3. Okay. Now what happens? Flip of 3 will become, so this function flips the information. Flip is 5 minus x. So 5 minus 3, the value becomes 2. You come back along this path, what is the value? 2. What is max of 2 comma 2? 3. Max of 2 comma 2 is 2. Flip becomes 3. You come back, value is 3. This becomes 3. What is here? 3. So again, so what is happening? No matter how many iterations you do, you will alternate between values 2 and 3. Now this is an intuitive thing because I am not going into details of lattice and all, but intuitively what is happening? Some information is coming along one path, some information is coming along second path, their meet gives you 2. The moment you apply your flow function, value becomes 3, but then when you come back, at this point the value becomes 3, but next time it becomes 2, next time it becomes 3. So this is not a monotonic framework. You are going up and down, and just like in many cases we saw, once you reached a fixed point, once you have reached a saturation, you stop. Here you cannot stop because every time, every iteration value is changing. Okay, that is the problem with data flow analysis framework if flow function is not monotonic. Okay, if flow function is not monotonic, there is no guarantee. You don't know how many times you will keep going around that loop. In fact, in this case, you will never be able to figure out whether you have reached a fixed, in fact, you are not even reaching a fixed point. Okay, so your round robin iterative data flow analysis algorithm, again, remember what I said in the morning. Your analysis might be correct, everything might be correct, but it is not a classical or it's not a traditional data flow analysis anymore. So traditional ways do not guarantee convergence, traditional ways do not guarantee termination. You have to think about having some non-traditional way of detecting termination. Now what could those different techniques could be? So just intuition, what can you do in such cases? To say, oh, I have done enough, now I want to stop. Suppose you end up having some analysis where it is really not possible to reach a fixed point, where it is not possible to reach a solution and saturate. What do you do? Again, intuition. So basically you use some counter, okay, you put a timeout. So this happens in many, not really data flow analysis, but network protocols. You put some timer, you put some counter, you put some way of acknowledgement or whatever. If you don't get it, or if you overflow or if you underflow, things like that. Okay, so you can have a x bit counter. The moment value becomes 2 to the power x, all bits become 0 and you stop. Okay, so something like that. So you have, again I am saying, once again I am iterating this. What you are doing may not be wrong, but then proving that it is not wrong is now your responsibility. You cannot refer to the book by Professor Khedkar saying that my analysis is correct. That book only works if you have followed the rules which are given there. That does not mean those are the only correct rules. So always remember this, okay? Just because something does not follow the rules does not mean it is wrong. It's just that we don't know about it. So it is responsibility, if you are going to use it, it is your responsibility to make sure it is correct, it is not going to have any harm. But if you stick to the rules, then mathematics behind this guarantees that there is no harm. Okay? Is this difference clear? And there are many such algorithms where you cannot prove correctness, even though intuitively they look correct, you execute them, you will never get a wrong answer, at least on the examples that you are trying. But that is like testing. You keep getting right answers, but maybe the day you are going to show your demo to your instructor, on that day it will create a failure, right? That happens. On the day of exam or on the day of demo things fail. Till then, last night everything works. So, but these things guarantee that won't happen. Okay, so we'll stop this part here. Last question we have to do tomorrow. This also quite, I made it simpler. This will do later. What is the time now? Any other questions? Otherwise, I may have to start a new topic. It's 5 o'clock. So we are stopping at 5:30, or what is the time? Yeah? 5:30, okay. Questions? If not, then we will go to so morning what we saw was simple constant propagation. Okay, it was very nicely written data flow analysis kind of thing. There are some challenge with that. One, it is too slow because you have to analyze every statement, do some kind of computation. The one which we will talk about, it is called sparse simple constant propagation. And why simple? Because it finds all simple concepts, all simple constants, which are same as our earlier. So our earlier algorithm, if it said a variable is has a constant value, current algorithm will exactly say that same variable has same constant value. So it is same as the previous algorithm as far as power is concerned. As far as efficiency is concerned, it is much more efficient. Okay. So here is a motivating example. The starting point for sparse constant propagation is a program in SSA form. For constant propagation, it was a normal program, 3 address code. So here you have a flow graph for a program in SSA form. So solid edges are like your program edges, but then we also add what is called def use chains or SSA edges. So can you guess what these dash edges are doing? The name itself tells you. So when do I introduce this dashed edge? It goes from definition to its usages. Okay. Now this is a very simple example. So every definition I think has only one use, but in general it can have, a definition can have multiple use, but there cannot be multiple definitions of a given variable. Okay. So looking at this program, what can you say about value of C3? Is it constant or not? Okay, what are different possible values or for C3? It can be 4 or 5. So if we start our morning constant propagation algorithm, it will say the value is not constant because on one path it is 4 and another path it is 5 and you are merging them. Okay, true. So when we do sparse constant propagation, again you will find the same thing, that C3 is not a constant. It can either be 4 or 5. Okay. What if I change C2 equal to 5 to C2 equal to 4? So morning program, again we will have C equal to 4 and C equal to 4 on both sides. So then it will say C3 is constant. This program will also, this algorithm will also say C3 is constant. Okay. How will it discover? So again, see, something becomes very simple. Once you have propagated constant values, and replaced variable by its value, you will have a phi function which will have certain arguments. If all arguments are same constant, the left hand side is the constant. If those arguments are either not constant or they are different constants, then left hand side is not a constant. Okay, so that is the idea, and in a way it becomes easier in in this SSA form. Okay, it becomes efficient because as you will see, we don't process all edges, all the information, we also jump along those SSA edges. In this toy program, those edges are very small, they are almost like going across one block, but actually they can jump over large number of blocks because they directly connect definition to use, which means you don't have to pass this value. So suppose the value of A is set here and used here. I don't have to pass that value through all the blocks. You can directly jump from here to here. You can directly jump from here to here. Okay, so which means in large programs, when there are fewer assignments or large number of usages, you save a lot of time. You don't have to do normal round robin iterative iterations. Okay, so is it clear? Motivation. This small program will not show you efficiency because we have as many SSA edges as there are normal edges and the sizes are very small. Okay, so how do we do this SSC? Sparse, simple, constant propagation, or first step, as I said, you have to have program in SSA form. In this, every basic block consists of only one statement. We add these connections called SSA edges. Again, it's very easy while you are constructing SSA itself, because you were doing renaming and all, you know where the definition is, where the use is. While constructing SSA, these edges can be added. So not much overhead there. These edges are also called def use chain in classical analysis. Okay, I am just putting it here because some places they will be calling it def use. Okay, how do you start your algorithm? So first thing you have to do is some initialization. So you evaluate all expressions which only have constants on right hand side. It could be 5 times 2, it could be 5 divided by 5 or whatever, and you evaluate it and assign the constant value to the left hand side. Okay, if I have x equal to 5 plus 3, I will evaluate 5 plus 3 at compile time and say x is a constant 8. If expression cannot be evaluated at compile time, let's say x is y plus 3 and I don't know anything about y, I will say it is not a constant. I am just putting this bar, it's a, I am at a very low stage. Okay, I am sorry, sorry, this is slightly different. No, if expression cannot be evaluated at compile time, which means x is equal to scanf x or input x, or x is some function which is not there in your control, then you say, okay, this is the pessimistic thing but correct thing, that I don't know about this expression, I will assign it a not a constant or a bot. Otherwise, every other expression you become optimistic, you say, okay, I am using this undef or optimistic constant value because I know later I will be processing this expression and figuring out whether it is a real constant or real not constant. Currently I am making it a special constant top. Okay, so pick up every expression in the program, do one of these three things and assign that value to the left hand side. You start with a work list. Okay, work lists are a very powerful concept in data structures or in algorithms. Why? So work list, they always maintain a record of things which have to be done from now onwards, and then you only do that work that produces more work, you push that at work list, you do that work that produces more work. But if you have a good analysis, this work starts converging, number of newly generated work keeps getting smaller, finally you are done. Okay, and in most programs you don't have to look at all the chairs or all the blocks or all the everything, because you only work thing which is required, only do work which is required. So initially, think about it, you have a program, certain expressions have been identified to be constant, okay, and you are doing constant propagation. So only these expressions are going to affect other part of the program. Something which is top, you don't even know anything about that expression, that is not going to affect rest of the analysis. If you don't know anything about this expression, wherever it is used, you won't be able to get anything about that. Okay, this is a problem with data flow analysis, classic data flow analysis. Even if you don't know about something, you have to carry it around. Here you only start with known information, something which you have been able to figure out and propagate it. That will create new such information, you propagate it further. So you only do the work which is necessary. So you initialize with SSA edges which are either 0.1 or 0.2, where you have been able to find a constant, or you are able to say, oh, this is definitely not a constant. Okay. The optimistic thing, you just leave it as it is, because it's not going to affect anyone else. And like any other work list, once your work list is over, you have processed all the nodes, you will be done. Okay. And note that work list is only with SSA edges, not with program edges. So should I draw it here? I think I might have it later. So how do you work? So you have certain edges where definition has turned out to be a constant or not a constant. So you just figure out this definition has a constant value or not constant value, some known value. Okay. You take that edge, what can you do? You have to propagate. Other side of edge is the usages, right? That's what SSA edge is. So you pick up the edge, you see, okay, the input has changed to this edge, so output, all the usages also have to be updated to say that, okay, I have figured out whether the expression contains a constant or not. So you update that. How do you update that? You take the meat of the value at def end and the use end for the variable defined at the def end. It sounds little, I don't know, twisted, but the idea is, what may happen, a value can go from constant to not a constant as you are discovering more and more values. Okay, so it could happen that at the use side you are saying x is a value 5, on definition side you are saying x is not a constant, so you have to update the use end. Other thing could be both side it is coming out to be 5. Okay, so then you have to keep it as it is. So take a meet, we'll see what that does. If the meet value, the new value that you have found, is different from the earlier used value, then you have to update your usages. So let me just again draw it little bit. So I have a definition of A, somewhere I have a use of A. There is an SSA edge. Let's say this is X. Okay. Sometime or other I decided, oh, A is a constant. Let's say A is equal to 5. When I discovered this, I will put this edge into my work list. Let's say this is edge E1. Somewhere I have maintaining a work list. I will put this E1 into work list. Later when I am processing, sometime I will pick this E1. I will check what is the value of A at the def end. It is 5. I will check what is the value of A at the use end. This might have come from some other definition of A. Actually, it won't happen because this is SSA, sorry. This is the sparse one, so it won't happen like that. But the use end, because previously I had not discovered A, it might be marked something else. Okay, so I have to compare these two values and update the value of A. Once updated value of A, I have to compute A star B again. Okay, so replace the value by meet and then recompute the def, the value of X at the use end. Okay. And what can happen? Again, this value might change. If this value has changed, lower means it goes from top to some constant value or constant value to a not a constant. Okay. Then any edge which is originating out of X, E2, E3, E4, I have to add them to work list. Is it clear why I am doing that? I got a new value for A, I computed A star B, I got a new value for X. So anything that is originating from X, now I have to tell them, oh, my value has changed. So I will put all those edges into work list. Next time I pick up E3, again I will check what is the value of X here, what is the value of X here. If they are not the same, I update it, recompute the expression, keep forward. So this is what work list based thing is. You do some work, it produces more work. You do more work, it produces even more work. But after some time, things will start stabilizing. Because finally your lattice is finite, you only move down. Okay. So when I say meet, what does it mean? Suppose my use here is a phi function. So let's say a1 is something and then later I am using it as some a3 equal to phi of a1 comma a2. So I have to figure out what is the meet. Okay. So meet is nothing but meet of individual components of phi function. This could be value 5, this could be value 7, this could be not a constant. So meet of all this will be not a constant. Only if all of them are constant, it will be a constant. Some of them may be top because initially you initialize them with top. So then top meet with 5 will be 5 because top meet with anything. So on one side I say I have not discovered enough, so I will wait. So I will keep it as an optimistic value. Okay, so like that. So again we'll come to some complexity. So constant propagation lattice height is 2, you can ignore that. You can only go from top to constant, constant to what? Only undef to constant, constant to not a constant. So you can only make 2 changes in constant propagation for a given variable or given value. So height is 2. In this case, when I pick this edge, okay, I am updating value of A here. As I said, this update can only happen twice. Okay, so any update can only happen twice, which means any outgoing edge I am only going to use it twice. So every SSA edge is examined only twice. So which means, okay, so and this is the size of SSA graph we talked about in the morning. It's the kind of number of nodes cross number of edges. So and practical is linear. So this thing means number of edges, it will be kind of linear in number of edges. So quite fast algorithm, and these edges are much lower, much smaller. Okay. So here is the example. Do you want to try it? Let me see what do I have. Okay. So we have to try it on the board itself. Okay, so what is the first step? You have to evaluate all the assignments in some sense. So for to make your life simple, all the assignments are kind of already evaluated. You know constant values and not. So initially all these edges, I think I should have numbered them there itself. There are only 4 SSA edges. Initially, this assignment, this assignment, this assignment, this assignment are evaluating to constant values. This is a complex expression, so we'll leave it at, this is a phi expression, we'll leave it at top for starting, okay. So these 4 assignments are non-top values. So we have to add what all edges to our work list? E1, E2, E3 and E4. Okay. Now once again in work list it does not matter which work you pick up first. But since we are doing it manually, we'll always try to maintain some order. So we pick up E1 and initially this expression will also evaluate to top because you don't know anything about these values, okay. So we pick up E1. What is the value of A at the def edge? It is 2. Value of A at the use edge, it is top because we have not seen it yet. We merge them, it becomes 2, 2 less than B. B is also top. So again, how you handle less than will define. In fact, this is not going to matter much because this is not an assignment. Okay, but then we pick up E2, similar thing happens. With E2 what happens? This branch, A less than B, you know that 2 less than 3. It evaluates to true, but then you don't do anything. Then you pick up E3. E3 is the interesting case. E3 says C1 value is 4 here, C1 value is top here. Okay. So you have to update value of C1, so it becomes 4. What happens to C3? This value is still top. Okay. The value of C3 becomes 4 meet top, which becomes 4. Note that we are discovering C3 as a constant 4 at this point, which is a wrong thing in the long run. But we are still not saying we are done. We still keep, work list is still not empty. Work list we have handled E1, we have handled E2, we are currently handling E3. So it's out of the work list. Okay. The moment C3 is computed as 4, okay, if there are any more edges C3 is used elsewhere, we will have to put all those into work list. Again, this is a simple program, not much. Maybe I can print a C3 here, put a print C3 here. So which means there will be an edge here, E5, okay. So I will have to put E5 in the work list. Okay. Next, work list still not complete. I have to take out E4. E4 says C2 is 5, C2 is top. I have to do a meet. C2 becomes 5. So I have to evaluate this expression again. So C3 now becomes okay, which is 4 meet 5, which will become NAC or bot in this case. Okay. Now note that temporarily we got a kind of wrong information, wrong thing, but that is not disastrous because we are not yet done. It is intermediate result. We only looked at part of the program. It's like again this optimistic thing. So maybe I will remain 4, but that's not the case. Once E4 is evaluated, you got C3 as bot. Interestingly, E5 has to be added to work list again, but then it already sits in the work list, so it doesn't get added. Now you pick up E5. E5 you just replace C3 by bot or you just ignore it because C3 is really not doing anything here. Okay. So as you can see, intermediate results were wrong, but finally once this work list completes, all your results will be correct. Okay. So C3 will come out to be bot or not a constant. Okay. You can add more edges, you can add loops and all and do some little complex. This is a very simple example because it is very difficult to do lot larger examples. But this itself will be interesting when we go for sparse conditional constant propagation. So second thing I want to do is, suppose I change C1 equal to 4 to C1 equal to 5. Let me, okay, so it was 5 here. So then E5 was added. Again, when I pick up E4, it will become phi of 5 comma 5, in which case you will discover this to be a constant 5. Okay. This time the value does not change, so you are not going to add E5. Okay. Why this matters? So let me just go back a couple of steps back. So when I process E3, I got a 5 here. I pushed E5 in the work list because I have to process it. Okay. Then, as I said, work list, it does not say you have to follow a certain order. You can pick up work in any order. Maybe you are using a stack. So you take last element. So now you process E5. E5 says, okay, you have to print C3, but it's actually not going to print, it just processes it. E5 is gone. Okay, so again it looks like we are doing wrong things. We are trying to print with a wrong value. But please understand, we are not actually executing the program. We are only updating values. Maybe something is using C5, it has on dependency, all those will get added into work list. But we are not yet done. Finally, sometime or the other, we will look at E4. Okay, and this value I will just change it to 4 for time being. So when I now pick up E4, C3 becomes phi of 5 comma 4, which results in not a constant, at which point I put E5 back in the work list. Note that first E5 because I discovered C3 to be 5. Second time E5 will get added again because now I have discovered C3 to be bought or not a constant. Okay, so ordering does not matter. If there is a change, I will refresh all the dependencies. Okay, so last time I picked up E4 first, so E5 got added only once. This time I picked E5 first, but then E4 changed E5 again, so I had to add E5 once again. So only when all elements of work list are done, I can claim my analysis is over. Now you use the result. In between, you cannot use the result. In between, you cannot change this print C3 by print of 5. Until that work list is over, you should not be changing any values in your program. Okay? You can do analysis with the new values, but values should not be changed, values should not be deleted till your analysis is complete. Only after this you will declare, oh, C3 is not a constant. Okay? In between, you cannot declare C3 is a constant. It's a temporary phase. Okay. Now the thing is, if you go back to our program, now let me ask you, if you look at deeper, what can you say about C3? If you really have to execute this program 100 times with different values of A and B, I mean not different values, in this case it's a forced value, it does not matter how you run this program, one of the branches A less than B is always true. Okay, so you will always be on the left branch. Again, very simple program, not very useful, but this happens in real program also. That's at runtime you discover certain branches to be not executable. Okay, if you could do it at compile time, basically if you could do a constant propagation of this expression will evaluate to be a constant true. If you can propagate it and delete those branches, then you get much better result. Why? C2 is never going to execute. Okay, C2 is never going to execute. But then how to capture this? You can't just randomly change your control flow graph. This might create a problem of monotonicity. Okay, so how do you handle that? That's what you can do using sparse conditional constant propagation. This is simple constant propagation. We are not taking into account conditions anywhere. Sparse conditional constant propagation, it is on top of that constant propagation along with conceptually I should say unreachable code elimination, or it identifies unreachable code and ignores it for the analysis. It's actually not going to delete it per se, that's dangerous. So it ignores definitions that reach a use via a non-executable path or edge. Okay, like we saw here. On the right edge, okay. So what should be the idea? What can we do? How can we improve this algorithm? I will start that tomorrow because in 5 minutes it will be difficult to cover it and take an example. So let's think about intuitively what can you do to detect that right hand side branch is not going to be executed. Tautology. Okay. So that you can do even here, but how will you use it? Yes, that is needed. So currently what was our goal? What was our methodology? Whenever this expression changed, we looked at all its usage and kind of tried to evaluate it. So whenever this expression changed or this expression changed, we tried to evaluate this. This change, we tried to evaluate it. Okay. We never looked at whether this branch is true or false. Can we somehow introduce that? And if so, how? So what does tell you about execution of a branch? How can you identify execution of a branch in this graph? Just stick to this graph. We'll generalize it later. We can execute it. Okay. Which one? A less than. Oh, you are saying if a comparison has a constant on both. So basically, if you can compare, if you can evaluate this comparison and you can get some value out of it. So let's say you get true or you get false. So what can you do then? Okay, good. So how do you ignore it? Okay. So so idea is that some kind of idea is emerging here. You don't want to evaluate this or consider this C2 unnecessarily unless you are guaranteed that this path is going to, or at least you have some chance of this path getting executed. If there is a guarantee that this path is not executed, you don't want to evaluate it. Okay. If I can guarantee this path is not going to be taken, you want to ignore C2 equal to 5 from consideration. That is the idea. Return, don't mix concepts. Where is return coming here?
Instead of A less than B comparison, we will write true.
You will write true here. That's not going to help you unless you can tell me that this branch is not going to be executed during analysis. Okay. So not only you have to consider SSA edges, you also have to consider program edges. And with every program edge, you have to have a flag saying it is executable or it is not executable. Okay. No, compile time also I can detect, right? If I can detect a compile time in this program, I can detect at compile time that A less than B is true. Always true. So I will mark this flag as 1, this flag as 0. If I cannot do it, let's say X is A is scanf, B is also scanf or input, then A less than B will be bought, in which case I will mark this as 1, this as 1. So that's in my hand. If A less than B is never evaluated, maybe this branch is never taken, then this never evaluates, these branches always get 0. Okay. So whenever you evaluate a conditional expression, depending on the outcome, you select branches which you have to execute. If it is a known true, you select only this branch. If it is a known false, you only select this branch. If it can be true sometimes, false sometimes, then you select both branches. Basically, this is not a constant. It's exactly the same thing. If it is a constant true, this branch, constant false, this branch. If it is not a constant, both the branches. If it is not yet evaluated, then you leave these branches as it is. Okay. So this is a simple change that we have to do in our algorithm. There is one more change we have to do. We have to change our meet. Earlier we were doing V1 meet, V2 meet, V3 meet, Vk. Now we say remove those V's where the corresponding branch is not tagged as executable. Pick only those V's where that I is part of your or tagged as executable, which has been marked that, oh, this branch can execute. Take meet of only those. So let's say this is 4, this is 4, this is 5, but corresponding branch has been marked not executable. So then you only take meet of 4, 4, you declare it as 4. Like the earlier case, it will be 4, 5, but 5 branch will be not tagged as executable. So 5 of 4 is 4, a single branch. Okay, so you have to ignore paths that are not yet marked executable with the hope that they will never get marked executable. If later they get marked executable, you will once again review it, you will once again evaluate it, at which point it will become non-constant. Okay, so that's what we will formalize tomorrow. But this is the key idea, and that's why you need 2 work lists. I will stop here. It's very tempting to keep going on. Okay, so tomorrow we'll look at how to maintain 2 work lists of SSA edges and also flow graph edges, and you have to juggle between the two to make sure you only mark those paths which are executable. Okay, thank you. So any feedback, any comment? Too dense, too light? At least you are able to get something out of the whole day. I know 8 hours, 6 hours is very difficult. You are probably doing 7 into 6, some 42, 45 hours in last 10 days. So it's difficult to retain everything, but at least retain those concepts, those intuitions. Those are what will help you devise a new analysis. All this you can get from books.